All right, so hey guys, my name is Sami and I'm from the London Clank team or Chrome for Android team. And I wanted to give you a brief overview of what we're doing with this project we call the Blink Scheduler. And so let's just dive right in. So the basic problem that we're trying to solve with this project is that the Blink main thread, the renderer main thread, is super crowded. Like there's lots of stuff going on there, and like basically that's fine. Sometimes you have a lot of work to do, but the problem that this creates for us when we're building this nice responsive platform is that there's certain high priority work that also goes to the main thread, like input handling and compositing work. And these tasks end up getting stuck behind all this other work that's going on. So the effect of this, and it's very visible if you ever used the browser on a phone, you try to scroll the page and it takes a long time to react and nothing seems to happen. So that's bad. And just to make it a little more concrete, here's a trace. I'm sure many of you have seen similar traces before. Lots of different things going on: resource loading, dumb timers, HTML parsing, lots of stuff. And why this is a problem in this case is, you see down here in the left, the compositor is posting a task to the main thread because it wants to paint a new frame. And it takes a whole second for that task to get executed on the right here, which is super bad. I'm told British people like queuing, but this is pretty extreme, so we should fix it. And we can see the same problem in our telemetry benchmarks. There's a couple of metrics that we're tracking. First one is this called queuing durations. It basically measures the same thing I was showing there on the previous slide. So how long does it take for the compositor task from when the time it gets queued to when it gets executed? And in this case, the median delay was 20 milliseconds, which is pretty bad. And another metric, a little higher level, is the mean input event latency, which means that how long does it take from when the system gives us an input event to when we give it to the GPU to be rendered. And like 50 millisecond delay is certainly noticeable in many types of interactions. And this is basically what the root cause is. There's all these components in Blink and elsewhere that want to do stuff on the main thread, and all of them basically act like they own the main thread. So they just post tasks to run there, and you get chaos. And that's the reason why we started this Blink project, to bring some Blink scheduler project, to bring some kind of sanity to this this whole setup. So the basic thing we want to do is perfect scheduling, which means that we do the right thing at the right time. So we're still running the same things on the main thread, more or less, but we want to do it in the correct order depending on what is most important and at each point in time. And one thing to notice that thing that we're not doing is trying to make everything run super smoothly. Like if you write a website that blocks in JavaScript for several seconds, we can't do anything about that. That's game over. But if your content is well written, it should be able to take advantage of good scheduling that we provide. So let's talk a little bit more detail about what this scheduling means and how these tasks are executed. So the basic mechanism we have there today is very simple. It's a first in, first out queue of tasks. So if you put your new task at the end of the queue, take the first task from the front of the queue and execute it. Simple as that. And the problem here is, again, that you put your high priority task there at the end of the queue. It takes a long time for that to get to the front. So what we want to do instead, we know that we have this high priority work, so why not add another fast lane for that work and let it bypass the other stuff so we can run it immediately. Seems reasonable. And we can also go and add more different types of queues for different types of tasks, so we can do more fine-grained scheduling. And that's essentially what we're doing. But there are some constraints that we have to be aware of when we're doing this, and I'll talk about a few of those. The main one is that a lot of these tasks that go on the main thread, they have implicit dependencies, like order dependencies between themselves and other work. So we can't just blindly go and reshuffle everything the way we want. And for example, you can't really composite the result of input processing before you have processed that input. Just doesn't make sense. And a lot of these assumptions are baked into code, especially testing code is often riddled with this, that it expects things to happen in a certain order, even though it doesn't always need to. So the way we solve this is that we only reorder tasks that we know about, like tasks that we know that are independent. So these tasks have to be explicitly opted into this system. And these are the different task queues we have for implementing this. So first of all, there's the default task queue where basically everything that we don't know about goes into. And then there's a separate queue for compositor work. That's both compositor work and input work, because they have to be ordered correctly. And within each queue, we maintain the ordering. So if you put stuff into the compositor queue, everything that was there before runs before that one. And the other advantage is that this gives a clear API for the clients of the scheduler, so they know which type of task are they dealing with, so it should go into this queue. So the next obvious question then is that how do you prioritize between these queues? Like, should we say that compositor work is always most important? I mean, it seems reasonable, and that's actually what we started with. But turns out you can't really do that. The problem was that we were regressing page load times by a significant amount, and the problem was that what happens during page loading is you get a bit of HTML, you pass it and insert it to the DOM, and that basically sets a flag that I want to composite now because the page has changed. And because we were prioritizing compositor work, we're doing more and more compositing and less of the actual page loading. So overall you were doing more work, so the page loading slowed down. So we don't want to do that. And the way we fix this problem is set the priorities dynamically. Don't have a fixed set of priorities, but instead look at the overall state of the system and use that to determine which work is important at any given moment. And there are some examples here. If we've seen user input in the recent history, that probably means that compositor tasks should be prioritized because you want to see the result of the interaction. And probably you can deprioritize some other stuff like resource loading. It doesn't matter that loading is a little slowed down in that case. And another example is because we know what the compositor is doing, we know when the frame has been drawn, and after that there's some slack time before the next frame begins. So we might want to do some background work, like idle work in that time period to move things along. So we call these different modes policies, and basically we're looking at different signals from the system and using those to determine the currently active policy. And some examples here, like input and the compositors events are used to choose these policies. And those policies then are mapped into these queues that I showed earlier, the priorities of those queues. So in compositor policy, you want to run compositor work first, and then only then attend to the default task queue. In the normal policy, you want to keep both default and compositor as equals. And for example, in loading policy, you might want to deprioritize compositor work completely. And one thing to notice, we can completely stop running certain types of tasks, like in the compositor policy, we don't want to do any kind of idle work because the user is actively touching the screen. We don't want to compromise that. So the next problem you run into, that even though generally you can assume that, for instance, this compositor work is going to be fast and it's going to be well behaved, but it's still possible to screw it up basically. So you can have a situation where you have so much compositor work that there's basically always a task queued up in the high priority queue. So you run that, you never end up running any of the other queues, so you completely starve all the other work, and that's bad. So we still want to be able to run or make sure that the other work makes progress, even though we think compositor is now the #1 client. So we do this wait round robin scheme where we every now and then check one of the other queues and see if there's any work to do there. So now I've talked a little bit about the constraints that we have, and next I thought I'd show a bit about of the architecture that we ended up with given all these constraints. And a big question that you have at the start is that where do you put this thing, the scheduler? And sort of an obvious choice because it wants to schedule tasks that come from Blink, like the Blink main thread. So why not put it in Blink? And that's what we ended up doing for the first version. But it sort of worked, but after a while it started getting awkward because we ended up having to re-implement much of the basic machinery of message loops and things like that because they don't exist in Blink. And posting tasks ended up requiring a lot of plumbing first from Chromium into Blink and then back out again. So you had to go through all these layers and ended up wrapping these tasks in this nested closures that weren't really efficient. So we didn't really like that solution and started thinking about other options. So the next version 2 was the idea that why not skip all the middlemen and just extend the base message loop directly so that we can do our scheduling there. And the idea is that you have the ultimate power there to do whatever you want because that's the message loop is the thing that decides what gets to run. But after a while, we sort of shied away from this because the message loop it's used everywhere. Like almost all the threads in Chrome have a message loop, and the code is kind of crafty and also very critical. So it's risky to go and mess with that. And any changes we would make in the main message loop for the main thread would be inherited by all these other message loops on other threads. So that's also not ideal. So from that we get to version 3, which is where we are at currently. The Blink scheduler lives in the content layer of Chrome, so not in Blink anymore. And it basically sits on top of the message loop. So the message loop is still in charge of running the show, but we sort of implement our own queuing on top of that. And the nice thing is that it lets us use all these nice building blocks from base to make our classes and functionality. And we don't have to cross all these layers that I was talking about earlier. So that's where we are at the moment. So now I can show some pictures about what architecture actually looks like. So remember we talked that we're providing these different task queues for different types of tasks. And then we have these policies which determine which of these task queues should be prioritized. And then finally we have the hooks into different parts of the system that get the events that determine the policies, like what is going on at the moment. So this translates to basically three key elements. First, we have the API that we provide to clients for posting tasks, and then there's the interface that chooses the next queue that should be attended to, and finally the mechanism that updates the policy. And to show the same thing in pictures, here's the classic message loop that is underneath everything. So you can use this message loop proxy to put stuff in there, and it gets executed in order. And the thing we add on top is this task queue manager. And internally, it has a number of different queues, and you can basically get a task runner that posts stuff into the corresponding queue inside the manager. And the manager deals with posting itself to the message loop and then running a task when that that comes back. And it's also important to note that there are still other tasks running on the same thread that don't go through the scheduler, which haven't been hooked up. So they're still going directly to the base message loop, and they're interleaved with the other work that we're doing. And here I'm just showing the different APIs you have for putting stuff into the queue. So Chromium side, you can get all the different task runners. In Blink, there's a scheduler class that you can use to post tasks, and also the default column main and post task APIs have been rerouted to go to the task queue manager. And the next thing we need is to decide which of these queues need to be serviced. So basically, when the task queue manager is activated, like the message loop comes back to it, it goes to this selector thing. It basically looks at the current state of the queues, like which of the queues have work, and decides which of those queues should be. Like it selects one of those queues from which the task to be run is taken. And on top of that, there's the scheduler itself that implements the policies and basically tells the selector what it should be prioritizing. That's basically the architecture. So what kind of benefit do we get from doing this? Well, we did have the version 1 landed for a while, and we did see some improvements to the queue iterations metric that I was talking about earlier. We didn't see much of an impact on the mean input event duration, but that was mainly because the page sets we had at the time, they weren't doing as much main thread scrolling, so it was compositor scrolling, so that bypasses the main thread, so you won't really see any impact there. But nowadays we have a little bit better page sets. There's this sync scroll variant of the spoonness benchmark, which basically disables compositor scrolling, so you always go through the main thread, and that sort of amplifies any improvements that you can make to the responsiveness of the main thread. And these are some preliminary numbers for the version 3 implementation. You can see the input event latency and the queue iterations are pretty well reduced. And on the right here, there's another metric that we have added. First, just to scroll update, which is a bad name, but basically means the first time after you loaded the page when you start scrolling, like that's the most difficult interaction to get right, because we may need to compile some JavaScript and like do things for the first time. So we see some improvement there as well. So we now have something that can prioritize compositor and input tasks over other stuff, which is nice. What are we gonna do next? So the other big thing that we've been implementing is support for what are called idle tasks, and this goes back to what I was saying earlier about after the compositor has done its work for a frame, there's this time period shown in green where nothing else is supposed to be happening, and we can take advantage of that and do some idle work and basically stop before the next frame starts, so we don't disturb any rendering for the next frame. And these idle tasks, the contract we have for those is a little bit special, because we don't know for a fact that there is ever going to be idle time, so you might actually end up starving these for infinitely long. And the actual API for them works so that when the scheduler calls into the idle tasks to do the work, it gives it a deadline, like point in time by which the idle task should yield or exit. So the idle task needs to keep track of time and not overflow into the next frame, basically. And there's a small subtlety here that if you post an idle task, it won't run until the next idle period, and that's because there's this corner case here that if you if we run the idle task and it decides it doesn't have enough time to do anything, it'll repost itself. And then we try to run it again, it'll repost itself. So we get this infinite loop at the end of the idle period. So we don't want that. And the first main customer for this idle tasks is the V8 garbage collection, and specifically the incremental marking step of that. And the advantage we get here is that if we do this garbage collection proactively, then that's work we don't have to do on the critical path anymore. So we're kind of making the critical path faster as a side effect. And the way it works is that V8 itself keeps an estimate of how many megabytes per second it can perform this garbage collection, and it looks at the size of the heap and the deadline given to it, and decides how much it can do this incremental marking. And if there's still more to be done after that, it'll just repost itself and keep doing something more in the next frame. And yeah, early results, we're seeing a pretty big reduction of garbage collection on the critical path from this. And we're also thinking of adding more clients to these idle tasks, like the sweeping phase of V8, and possibly some optimization work could also be done here. And we heard about HTML parsing yesterday. That's another potential client, as well as oil pan garbage collection. Another thing we're considering is maybe doing something special about loading tasks that have to do with loading new content on the page, because right now they're really running at random times, and you can't really predict when you're getting resource callbacks. And the idea is to add this new policy called loading time policy that basically lets us prioritize different things depending on the loading state. Like, for instance, if you're just starting to load the page, you might want to prioritize loading until you get something on the screen, and after that, maybe prioritize something else. And yeah, in the spirit of BlinkOn, I listed some half-baked ideas as well that we've been throwing around. The first one is not really directly related to the scheduler, but I'm sure many of you may not know that when you do set timeout 0 from JavaScript, it actually gets rounded up to set timeout 1 internally. So you always get at least 1 millisecond of delay. That's bad. Like, there's no reason to do that. And if we fix that, we can enable web developers to do more fine-grained scheduling of their own on the main thread. And maybe we want to actually give some kind of idle task primitive or any other scheduling primitives as an API for the web. Another thing is that once we have more knowledge about what's going on in the different renderers, we might try to do things like synchronize idle tasks and timer wake-ups between renderers, so you don't get this random storm of wake-ups because everything's running unsynchronized. And finally, maybe we want to give developers more feedback about what they're doing. Are they hitting the deadlines that they should be? And if not, we can show the red dragon that we were talking about. So what did we learn with all of this? We learned a lot. So it's really easy to get this stuff wrong. And there's lots of unintentional dependencies on ordering all around the code. So what ended up happening is we turn on the scheduler and something broke. We had to look into it and then try to turn it on again and do this iterative process to get everything moving forward. And there's a lot of subtleties, like new exciting things you have to learn about, like nested message loops and how do we shut down Blink and where all the different heaps live and stuff like that. But fingers crossed, I think we have it sorted out now, so we know what the constraints are. And actually the whole process of landing stuff and figuring out what broke was a good way to make at least some incremental progress. And because the way the branching works in Chromium, we could do this safely without actually breaking end users. And also keeping a close eye on the different metrics, even the ones that you weren't really meaning to change, like page load time, is useful. And as a practical thing, having local context here in Mountain View, like sort of championing our work and making sure we have the right people to talk to, that was really valuable. So thanks, Eric. I don't know if you're in the room. So final slide is basically me trying to guilt trip all of you to doing our work for us. So we can't really fix the world by ourselves. And like I think I forgot what you called the diagram, but the different timing constraints, that's a great way to get everybody thinking about this stuff. But I'd like to add a few more things on top of that. So as a general rule, if you can help it, don't hang on to the main thread for very long, because we can't interrupt you. Like, you own the main thread as long as you're sitting on there, so we can't do anything else. So try to keep your tasks short, and if you have long-running tasks, consider breaking them up into incremental chunks, so you can yield in the middle. And to make that easier, we added this API called should yield for high priority work. You can call that from within your inner loop and see if there's something else that you should basically get out of the way and continue your own thing later. And you can also try to put your work into the more appropriate queue instead of just use the default one. And maybe we need to add a new queue for your stuff, who knows. And finally, there's this nice idle task API that you can use if your workload sort of fits into that model. And yeah, we have this new scheduler dev team that's basically set up to track scheduling issues both in Blink and also in the Chrome compositor. So if you're interested in either of those, sign up and get involved. And that's basically the end of my talk. Any questions or concerns? In the back? So let me see if I got that right. So you're asking if we tried to change the priority depending on how long work had been sitting in the queue. Yeah, we sort of considered that. We wanted to start with a simpler model because like we did some research into other schedulers, like the Linux BFS scheduler, I think works like that. So maybe that's something we want to do going forward, but we just wanted to start with something really simple. Yep.
I had two questions. The first one is, how much stuff in Blink is using this? Is like everything going to the default queue now, or is there still stuff that's getting posted directly to the message loop?
Right. So the question was how much stuff in Blink is using this at the moment. So basically everything in Blink is going to the default queue by default at the moment. So you can't get to the main message loop anymore from Blink. For the idle tasks, only the V8 is hooked up at the moment, but you could add other stuff.
And are all tasks that are running on the render main thread all running inside the scheduler? Is there anything that's coming from the IO thread that's running?
Right. So at the moment, we still have problems on the Chromium side. Like, as you said, IPC is going directly to the main message loop. but we're actively working on getting that scheduled as well.
I got a question about, it was related to this delay thing. Have you had any problems with idle stuff getting delayed too much? Do you have things you thought were idle, but they actually needed to be somewhat higher priority, or do you have a pretty good, like how much has, yeah.
So have you had problems with idle tasks getting delayed too much? No, because at the moment V8 is the only client, and actually it copes fine with not getting any idle time at all. So that just means that you have to do the garbage collection in the critical path. So that's also bad, but at least things keep working. So no.
Okay, but that's the only
right. Okay.
Did you say how much like peak memory usage?
So question about V8 peak memory usage. I think I need to defer to Ross or someone. So we don't know. Right, so we're not expecting huge changes to the heap size in any case. In the back?
Yeah, the HTML specification has this notion of task sources. For example, there's the dominant task sources, there's the network task sources, there are media element task sources, and none of these actually exist inside of that's a single task source. Have you thought about making those explicit and scheduling them differently? And if so, one thing that can happen is that since all of those are now a single task source, there's a well-defined order where the spec says it might not actually be well-defined, and the spec says that the kind of that problem you thought about.
Right, so the question was about how the spec defines these different task sources and like how those could get executed out of order, and right now they don't because they always go to the same underlying thing. We haven't gotten that far quite yet because we started out with compositor and input tasks, which are sort of totally separate and driven by completely different primitives. Definitely going forward, like one of the things we're trying to do right now is trying to identify like the next set of problems that like problem tasks that we want to split up or delay or handle differently. And I'm sure we'll get to things like you described that we might want to do something in a different order, which might be actually visible to the web. Last call. All right, thanks.